Hey guys, this is a video that is going to take us through Experiment 22 or the Thermodynamics workshop. And I apologize, I'm sitting outside, so if you can hear some planes and birds chirping, hopefully they're not too loud and distracting, so sorry about that. So what we're going to do is we're just going to go through some just basic concepts, and I'm going to do a couple of the problems in the first section of this workshop, and then after that, you guys are going to go through and do kind of the problem set of the lab itself, and you will submit your answer sheet and your work that you used to do those problems as your report form and post-lab questions. So first off, what we're going to do is just kind of give you some basic pieces of information. And when we're talking about thermodynamics, we need to kind of talk about some things like standard states. What does standard enthalpy look like? What kind of conditions are required to be present for you to have kind of standard state things? And the standard state for a pure substance in liquid or solid is essentially set as 0 value for the enthalpy or change in enthalpy for that substance. And we use a kind of a 0 that's subscripted, and we say Nought, or N-A-U-G-H-T, to refer to that value. So I would say delta H naught equals 0. For gas, the standard state it has to be at 1 atmosphere or pressure, or 1 atm. For solution, then that concentration is going to be 1 molar, and we might write that as a capital M. And by convention, if you're talking about a substance and the formation of that substance from elements, from the elemental form of that substance, then the delta H value of any element in a substance is 0 as well. So how we actually calculate the delta H's for reactions is something that we call Hess's law. And there are several different ways in which to use Hess's law to figure out the delta H of that reaction. But essentially what it is just a summation of each of the delta H naughts for each kind of stepwise reaction in the series to get that reaction. And so what we're going to do is we're going to do a couple of examples of how that works. So for problem number 4, what we're going to do is, as an example, we're going to use Hess's law to consider the following reaction. So what we want to do is essentially figure out what's the delta H naught for this reaction here, but you're only given the information from these 3 reactions in order to determine it. And so the way that we do this is essentially we're going to build this reaction using these up here. And so how you do this is what I do is start on the left-hand side with the first substance. And this is carbon in graphite form. It is important to note that because there are several different forms of carbon, and the values of delta H of formations and any reactions that come with it will be different based on that particular distinction. So what I'm going to do is I'm going to find this particular substance in any of the 3 reactions up here. It turns out this first one has it in there. And what I want to do is I want to write that equation down, but I want to write it down so that the carbon graphite is on the left side of the reaction, just like it is on the left side of the reaction that we're interested in. And it turns out it's already written that way, so we just write it like this here. And then we'll write all of the rest of the stuff that goes along with it, although we're not really concerned with it at this point. And what we'll do is we'll also write down the delta H naught value that's associated with it, just like this, with the units and the sign and everything. Since we wrote the reaction down exactly as it's listed here, we don't change anything about it. And in fact, you want to ensure that the amount in moles that is listed here is equivalent to the amount that's listed in here. And it turns out that this is a 1 right here, and this is a 1 right here. So they're the same, so you don't really have to do anything to the reaction itself. It stays as is, so the delta H naught value stays as is. And I'm going to show you how this changes later on. So what we're going to do is just go ahead and go through, and let's figure out, is there a reaction that has this substance, this next substance in it, that's H2. And it turns out, yes, the second reaction here has H2. So what we're going to do is write that reaction to where H2 is on the left-hand side, just like it is on the left-hand side here. And so we'll write that down, H2 plus 1/2 oxygen yields H2O. But this is where, and we're going to write down the delta H naught, just as is, negative 285.8. You got some nice birds chirping in the background. But here's the problem. If you'll notice, in this reaction that we're building, there's 2 moles of hydrogen, but see, this one only has 1. So we're going to have to make use our reaction that we're using to build this guy have the same number. So what I do here is I'm going to have to go in and I'm going to have to put a 2 here. But here's the deal. If you do that to one substance in this reaction, you have to do it to all. So I'm going to put a 2 here. I'm going to put a 2 here. And I'm going to have to multiply times 2 times this value to adjust for the amount of kilojoules that is going to be created, because originally this is kilojoules per mole and you only had 1 here, but now you have 2, so I'm going to have to adjust that. So essentially what you're doing, it's kind of like if you had a mathematical equation and you multiplied 2 by one side of the equation, you have to do that to everything else in that equation as well. So it's kind of like a mathematical principle as well. Okay, so now that we've got carbon and hydrogen done, now let's go through and look for CH4 or methane. And it turns out this third reaction has methane in it. Turns out right here. And that's great. But the problem is that methane is on the right-hand side of the reaction in the one we're trying to build. It's on the left-hand side in the one we're using. So we're going to have to put it on the left-hand side. And all you do is just flip what's considered reactants and products for the entire reaction. So what I'm going to do is I'm going to come over and I'm going to take all the products in this and make those reactants, and vice versa for the other side. So I'm going to write CO2 plus H2O yields CH4 plus O2. Make sure we get the right coefficient. And our delta H we will write down just as is, given to us above. However, I flipped this reaction. If you flip the reaction, you have to now flip the sign. So I have to come over here and make that a positive. And that's fine. You can do that. You just need to make sure also that you have the same number of moles that's in this built reaction as you do in your problem. And it turns out it's 1 and 1, so we're good. So we don't have to do any multiplying. So now what you do is you go through and you sum everything up. And what I mean by sum is you're summing all the reactants and products on both sides of the yield sign, and then you're summing your delta H as well. And this delta H ends up being the delta H for the full reaction that you've built, not just for each individual component or step of the reaction. So let's look at how we can make this guy get built or kind of cancel out or whatnot. So it turns out that carbon, this guy right here, is the only carbon in this reaction, and so that will stay. It turns out, if you look, there is an oxygen here and essentially 1 oxygen here, because 2 over 2 is 1, right? So we could just kind of cancel that and put 1 here. If there are two oxygens on the left-hand side of the reaction and there are two oxygens on the right-hand side, they cancel each other out. So this goes away. All right. Now, is there anything else that does that? It turns out that there are a CO2 and a CO2. They will cancel. There is two waters. They will cancel. And then everything that's left over, you have two hydrogens and a methane, they don't cancel out. So you write what's left over as your built reaction. And guess what? That's what you were trying to make to begin with. It looks exactly the same. So if it looks exactly the same, then you know that you've done this correctly. So now what you're going to do is you're going to pull in a calculator and you're going to sum up all of the parts of your delta H naughts, making sure that you have the correct sign and the total amounts of those. So let's go through and do that. So I have negative 393.5 plus 298.8 times 2, and that should have been negative, so let's make sure that I write that correctly. Let's do that in a different way. Let's do our 285.8 times 2 equals 571.6. That should be negative, okay? So I'm going to make that negative, and then I'm going to add that to my now negative 393.5. So that, let me make sure. Let me put that one more time. My calculator is a little finicky. I'm going to add that to my negative 393.5. There, we've got that correct now. And now we're going to add that 890.3. There. All right, there we go. Let's pull that back up. This is negative 74.8 kilojoules per mole. And so this value is the value that this entire reaction up here should produce. It should give off 74.8 kilojoules. And how do I know it gives off? Because it's a negative value. And so that's an exothermic reaction. Now, so what I would like for you guys to do is we're going to go through this next problem, and this still uses Hess's law. But this time I'm just going to kind of pull a few things in that are a part of that delta H naught of formation values. And so essentially, I have given you values. These values you can actually look up in your textbook, but I've already written these down. These are delta H naught values, but they're formation values. It means that to build this particular compound, they were built from elemental forms of each element that makes that substance. And what I want you to do is use those reactions that we're going to kind of write really quickly and their delta H naught of formation values in the same way of this problem above to calculate the delta H naught of reaction for this reaction. And so it's essentially what I'm having you do is make these reactions without me giving them to you. And then I've already given you the delta H naughts, and then we'll go from that and do the same kind of problem. So let's go ahead and write those down here. So for number A, or letter A, is C2H5OH. So C2H5OH. Make sure that's correct. Yep. And so what we're wanting to do is build that. Well, you just build it using the elements that it's included in it. So you have carbon, you have hydrogen, and you have oxygen. But when we're writing them down as elements, they have to be in the proper elemental form that they occur naturally. For carbon, we're going to use graphite as our kind of go-to for carbon. Hydrogen, this is going to be H2 because hydrogen is a diatomic molecule, and this is going to be in gas form. at room temperatures. That's the temperature we're assuming. And oxygen is also diatomic and gas at room temperature. And this particular one, it doesn't say, we're going to assume actually that this is in liquid form just because it's written as liquid up here. Okay, so that is the reaction. We wrote it from the elemental forms. The delta H naught of formation for this particular substance is equal to negative 277.7 kilojoules per mole. There you go. Now we want to do the next substance. This is water. So we're doing H2O. We're probably going to be using the liquid form there because that's when it's in our formula. And what two elements make up water? Well, hydrogen and oxygen. They are both going to be diatomic, and they'll be in gas form. Okay? And the delta H naught of formation for this is negative 285.8 kilojoules per mole. And our last substance that we're going to build is C2H4. Two elements, carbon, hydrogen. Carbon is going to be graphite. Hydrogen, diatomic, gas form. And we're going to use C2H4 as gas. Delta H naught of formation for this particular substance is plus 52.3 kilojoules per mole. So that's how you would go about writing a reaction, a formation reaction for a particular substance. If you didn't know it already, it's just a matter of just building it from the elements and making sure the elements are in the right kind of phase and right diatomic if it's needed. One thing that you need to make sure that this happens though, or that occurs, is the fact that you make sure that they also are all balanced. So now I'm going to go back, now that I've written all of them, I'm going to go back and make sure that they all balance. But I need to make sure that they balance to a point where this value or coefficient in front of the formed substance is 1. So what do I do to make that happen? So carbon, for this first one, I know needs to be a 2 because there are a total of 2 on the right-hand side. Hydrogen, there's 5, 6 total, and I have 2 here, so I just need to multiply this times 3. But I want you to look here. This has 1 oxygen, and this has 2. Remember, I can't change this guy over here. It has to stay that way. So what am I going to do? How do I get a 2 to be a 1? Well, and I can only use a coefficient here. Then what I'm going to do is I'm going to just divide it by 2, which is essentially the same as multiplying by 1/2. So that's where you're seeing the 1/2 come from. And it's because I have to maintain a 1 here. Why? Because the units are kilojoules per mole of forming this substance. So this has to be a 1. So let's go do the same thing for the rest of these. So right now I've got 2 hydrogens, 1 oxygen. I need to put a 1, so I need to divide by 1/2 or multiply by 1/2. And then over here, the next one, I have 2 carbons. I've got 1, so let's just go ahead and put a 2. And then I've got 4 over here on the right and 2, so I just put a 2 here. That's pretty easy. So that's how that works out, and you would use those reactions as is to do the problem on the next part. So for this one, this number 6, it says determine the delta H naught for the reaction expressed in equation 6. And what we mean by equation 6 is this little guy right here. This is equation. So we were trying to figure out what's the delta H naught reaction for that particular substance. But we're going to use the reactions and the delta H naught values from this section. And so essentially we're doing a second problem that we just did that was done in this particular one above. So again, we're going to want to build this particular reaction. So C2H4 plus water yields you ethanol. So C2H4 plus water yields C2H5OH. And we'll put our signs here as well. And we're just going to use the reactions up above. So let's start with C2H4. That means we're going to use this guy. We're going to flip it so that we can write it in the correct way. And I'm going to use a different color. So I'm going to put C2H4 yields carbon in graphite form plus H2. And make sure that I have the right units or coefficients. And now I'm going to write my delta H naught. 52.3 kilojoules per mole. And I flipped this. So what do? I flipped the sign. It went from positive to negative. Okay, so check. Got that one. Water. That's the second one. So we're going to flip that one as well. So H2O yields H2 plus 1/2 O2. Delta H naught of formation is negative 285.8 kilojoules per mole. I flipped. So what do I do to the sign? Flip it. Okay. Got that one. And they're correct coefficients as well. So C2H5OH, we're going to use this one. And that one stays the same because it's on the left-hand side. So we'll put 2 carbons that are graphite plus H2 plus O2, and I believe it's a 3 and a 1/2 yields our substance, C2H5OH. Delta H naught of formation is the negative 277.7 right here. And we didn't flip that one, so we leave it the same. Now, if you'll notice, I tried to kind of sort of keep our yield signs in the same spot. And now what you do is just to add everything together. Make sure that you built it correctly. We're going to cancel out our graphite here. You do 2 of those, 2 of those. We're going to cancel out our 3 hydrogens. We're going to cancel out 1/2 of water or oxygens, and that leaves us left with these guys. So C2H4 plus H2O, C2H5OH, and boom, that's the exact same thing as you see here. So we're now just going to pull it in our calculator and add everything up. So you have negative 52.3 plus 285.8 plus negative 277.7, negative 44.2 kilojoules per mole. So this would be exothermic because you're giving off energy for that reaction. Okay. All right, so now there is a shorthand way to solve for this type of delta H naught of reaction for a substance. And that is if you happen to know the delta H naughts of formations for each substance in a reaction. So what I mean in using the formula that looks like this. This is a shorthand way. You may not always be able to use this, but if you have the values for it, you can. So what you would do is you would sum up multiplying the moles of the coefficients in the balanced reaction times the delta H naught of products. You'd add them all up, and then you're going to subtract the sum of all of the delta H naughts of the reactants, keeping in count the number of moles. And so let me show you how to do that using this equation here. NH4 NO3 yields N2O and H2O. Now, in order for you to do this, you have to know what the delta H naught of formations are for each of these substances. And that wasn't given to you in this particular handout. There is a way that you can find them out. There's 2 ways. You can look them up in your textbook. So if I pull your textbook up, and we look at this back here is an appendix in the back of your textbook. It's the standard thermodynamic properties. They have delta, this first column right here is the delta H naughts of formations for any substance. And what you do is you look by element. So A lot of these have nitrogen in them, so let's just go to N. And so you have to scroll. There's a lot of them in here, so you just kind of just scroll down. And you just try to find that substance. So we're looking for NH4NO3 that's solid. And it turns out that that value that you get from that is negative 365.56. And then and let me move that. It's the very first one below the green there. And that's your negative delta H, or your delta H value for that particular substance formation. So we want to do N2O. So let's look for N2O. And we want to make sure it's gas. That's 81.6. And then what we want to do is look for water. And so it depends. It could either be hydrogen that it's under, or it could be oxygen. And so we're just at oxygen, so it didn't look like it was there. So we now go for hydrogen, and it looks like, oh, there it is, H2O. But see, notice how there's one for liquid and one for gas? You have to choose the right one. See, the values are different. So we're going to choose the one for gas, and that's negative 241.82. All right, so that's how you do that. So now what you do is you just literally plug them into this formula. So the delta H naught of reaction is going to equal the sum of all of your products, that's this side over here, times each one of them times their coefficient, okay, or the number of moles, or N. So I'm going to take the first product, and it's 81.6, and the N for it is 1. So I can take 1 and multiply it if I want to, or you could just kind of assume that you know that 1 times the number is that number. And then you're going to add that to the second product, and that the coefficient here is 2. So it's 2 times negative 241.82, and that's your product side. And you're going to subtract from that all of the reactants, and it turns out there's only 1. But it'll be 1 times negative 365.56 because the N is 1 for this particular substance. And so it's just a matter of you plugging those into a calculator. And let me pull up a calculator here. And here we go. So I'm going to do kind of this section first. So 2 times negative 241.82. And then I'm going to add that to 81.6. And that should give me a value of negative 402.04. And then I'm going to subtract this value, which is negative 365.56. So essentially that's adding, if you will. Or we can put that down here. And it looks like this. So plus 365.56, negative 36.48. And all of these are kilojoules per mole. So that's a simple way, shorthand way to do the exact same thing that we've done up here. And you could have done that for this reaction because you knew the delta H naught of formations for each substance in that reaction, and you would have gotten the same number. Okay, so there is an additional way in order to find delta H values, but it's not using enthalpy. Is using this thing called bond energies. And bond energies are essentially the amount of potential energy located in a bond between 2 atoms. And so it's as simple as subtracting the sum of the bond energies associated in every bond of any of the product's molecules from the sum of the bond energies of the reactants. And so to do that for this particular problem, there's a little bit of typo there, so kind of forget that. You kind of sort of need to draw this substance. And it looks something like this, where you have 2 hydrogens attached to each carbon, which they are attached through a double bond. And you're going to react that with 2 bromine atoms attached together to yield a substance that looks like this. And it doesn't matter kind of where the hydrogens and bromines are attached to each of the carbon. They could both be on top or both be on bottom or staggered, kind of like what I did now. It doesn't matter. You just care that they're there. And essentially what you would do is delta H naught of reaction is equivalent to the energies that are associated with each of these types of bonds. Well, you need to know what the values are, right? And so there's a very easy way to do this. You just look them up in your text, and I happen to have an image for them, and they look something kind of like this. And so these are some standard values for the types of bonds that we may see. And so what we'll do is we'll look up all of the bonds that are there, and we'll just add them all together. And so the number of bonds I have that are carbon-hydrogen, there's 1, 2, 3, 4. Out of all of your reactants present, all of them. And so I need a carbon-hydrogen bond value, and that's right here. So 415, and they are in the units kilojoules per mole. And I'll multiply that times 4. The other bonds that I have is I have a double bond carbon-carbon, and go find that. That's right here, 611. And that'll be times 1 because I only have 1. And then I happen to have 1 bromine-bromine bond. Single bond. So how much is associated with that? Right here, 119. Or 190, sorry. And I only have 1 of that. So you would add all of these together, and that would give you that value. Well, let's go ahead and do the product side as well, and then we can just plug all of those into the formula. So we have carbon-bromine, carbon-bromine. And we've got 2 of those, so we have to look those up. Carbon-bromine is right here, 275. Carbon-hydrogen, again, same thing, 415 as previous. And it turns out, so we have 2 of these, we've got 2 of those as well. And then we have 1 carbon-carbon single bond. Carbon-carbon single bond is here, 345 kilojoules per mole, and we've only got 1. So let's do some math and kind of sum all of these guys up. So 415 times 4 plus 611 plus 190, that's 2,461 kilojoules per mole for all of your reactants. And then 275 times 2 plus 415 times 2 plus 345, that equals, over here, 1,725 kilojoules per mole. Okay, so we've got those values. So again, keep in mind the actual equation is reactants minus products in this particular case. So reactants are the 2,461, and we'll subtract the products, it's 1,725, and that value should give us the number of kilojoules per mole of our enthalpy of formation. Oh, and I kind of cleared that really quick. 742 kilojoules per mole for that reaction. So this is your answer. So there is an alternative way. If you don't know the delta H of formations for substances, you could just use bond energies as well. Okay, so in this particular kind of problem, what they want you to do is go ahead and do this exact same thing, calculate using bond energies for the formation of hydrogen gas. So that means we're forming HCl gas, and you need to do that from H2 plus Cl2 because they're both diatomic. And we would have to balance this, we would have to do this. But remember, delta H naught of formations for substances are per mole of that substance. So we can't put a 2 there. We have to divide it by 2, divide it by 2, divide it by 2. So the real way to write this equation is really 1/2 hydrogen plus 1/2 chlorine yields 1 HCl. So this is the proper way to write that. So given this, though, what you would do is to go ahead and use bond energies to tabulate that. Now, since there's a 2 up here, the way that this equation works is you could still use this same equation, and it wouldn't really matter if you wanted to use it written this way originally without having the divide by 2. You could, because that goes ahead and takes care of everything that's there. Or we could go ahead and just go ahead and use the proper way to do that. Whatever bond energy you had here, you would just multiply by 1/2 when you sum everything up. Okay, so the last part of this problem video is we're going to talk a little bit about, or this is actually the second to last thing, is the entropy. And entropy, we just wanted to give you a couple of little pieces of information about it. Is kind of a fairly abstract concept, but see if you can follow what we're talking about when we talk about entropy. Essentially, what it does is it represents the unavailability of a system's thermal energy to be available for conversion into mechanical work. And so, a lot of times when we talk about entropy, we talk about it how it's really considered the randomness of a system. You might even see it referred to more often as the disorder of a system. In fact, probably most of the time we talk about it as, entropy is just the measure of disorder of a system. Well, entropy, anytime a reaction happens, or even if you're looking at a substance, the measure of disorder will always increase. And so that means the entropy always gets larger. And so as a reaction proceeds forward. And so it's something that is a little bit of an abstract concept. We can't really technically measure it directly. We do measure it in changes in entropy. And there's a couple just like little tidbits of pieces of information about it that you need to know. Crystalline substance, the entropy is 0 at absolute 0. And we can still use the same principle of Hess's law of subtracting the summation of all the products minus all of the summation of all the reactants as a way to determine the entropy for a reaction. So we're using kind of the same principle, just different values that have different units. And so if we were doing that for this particular reaction, we need to know what those entropies are. So the delta S naught of these particular substances. Well, where do you find those? That's where you pull your textbook back in. In your textbook, you use the same kind of chart that you use for delta naught of formations, but we're going to use the third column that are delta S's. And if you'll notice, the units are joules per Kelvin mole. So they have slightly different units than the entropy problem, or enthalpy values. So what we're going to do is we're going to look these substances up. So we're going to look up N for nitrogen. That'll help us find, let's see, I didn't quite go far enough. Here we go. So we're looking for N2O5. That one right there is the top one. So we're going to third column, that's 355.7 in joules per Kelvin mole. So now we're looking for NO2. There we go, in gas form, third column, 240.1 joules per K mole. And then we're looking for O2. There we go, gas form, 205.2 joules per K mole. Okay, and so what we'll do is just plug them into this formula. The delta S naught of the reaction equals the sum of all of your products. So that's 4 times 240.1 plus 1 times 205.2. sum those together, and then we're going to subtract the sum of the reactants. So that's 2 times 355.7. And there's only one reactant, so we'll just put that there. So let's do some quick math. And 4 times 240.1 plus 205.2, that's 1165.6, minus 2 times 355.7, 711.4. Sorry about the plane, it's a little loud. So let's do some math. Figure that out. Here we go. 454.2 joules per Kelvin mole. So this is how you would go about using kind of other thermodynamic values to figure something out about a reaction. All right. So now let's go to the kind of the last concept, and this is using another thermodynamic value called Gibbs free energy. And Gibbs free energy is something that takes into account enthalpy and entropy along with the temperature of the reaction. And it turns out that based on the sign of the Gibbs free energy, or delta G, we can determine whether a reaction can spontaneously proceed forward or not. And so the kind of the rule of thumb is that if the delta G is positive, it's not spontaneous, which means you would have to do something to make the reaction proceed forward to make a product. You would have to apply some kind of catalyst or change the conditions of the reaction. Sometimes the temperature would be enough in order for that reaction to happen. If the delta G is negative, it is spontaneous, and that means if you just put the products together, they're going to form, if you put the reactants together, they're just going to form products. It doesn't matter what you do to it; they're going to form that. If you're at 0, though, you're just neutral and nothing's going to happen. They wouldn't react anyway. Okay. Standard state's kind of the same. 1 atm, 25 degrees C is your standard state. Any element, the standard state for that is delta G is equal to 0. And we use kind of that Hess's law type equation to find delta G as well. And so if we wanted to see this reaction and figure out what is the delta G naught of this reaction to figure out if it's spontaneous or not, we can just use these guys and this equation to do that. And I know it says show your work on the next page, but I'm just going to do it here. So we do delta G naught of the reaction is equivalent to your product, sum of your products. So that's negative 261.90 plus negative 51.57, and both of them are times 1. So I just kind of left that off if that kind of confused you there for a second. And then subtract the product, and this is also a coefficient of 1. So I'm just going to subtract the negative 286.06. And so if we pull our calculator back out again, so it's negative 261.9 plus negative 51.57. It gives you negative 113.47. And then we're going to subtract negative 286.06. And that total gives you negative 27.41. And this is, the units for these are kilojoules per mole as well. That's negative. So since it is negative, is this reaction spontaneous or non-spontaneous? And that's kind of the negative 27.41 kilojoules per mole. That's what these lines are for. Is it spontaneous? Absolutely, because it's negative. Okay. There is another way to figure out the delta G if you don't know the delta G values for each substance. If you happen to know the entropy and enthalpy, sorry, that said that the other way, the enthalpy and entropy, then you can actually figure out the delta G for that reaction as well if you know the temperature. And so you can just use this formula right here. And so the delta G naught for the reaction would equal the enthalpy negative 52.50 minus the temperature, but in Kelvin, so you add 273 to that, that's 298 K, times the negative 175.083 for the entropy. And that would give you a value that looks something like this. So 298 times negative 175.083. Okay, so we get a fairly large number. I'm going to write this down. And then I'm going to do some math here. I'm going to do negative 52.50 minus negative 52.17. And we'll just go out to 3 decimal places here, equals. So that's negative 0.326. And again, kilojoules per mole. I left off the units here, but you guys should probably keep your units in here when you're writing these problems, so you know that everything's subtracting and canceling out correctly. So the question is, yeah, we've got a negative delta G value here. Is this spontaneous? Yeah, it's negative, so it is. All right. So those are kind of how you do those problems. The next thing you want to do is go through these problem sets. There's a couple of things, just, make sure that you box your answers. Make sure you write everything in a way that's legible that I can read. And then you're going to put all of your answers on this sheet of paper. And what I will do is, if you get the correct answer, that's great. I just won't look at your work. But if you get an answer wrong, that's where I need to go back and look at your work to see, kind of where you messed up so that I can give you feedback. So make sure that after you write all of your answers on the answer sheet, you submit the answer sheet along with your work on the back. This sheet here and your work, your scratch paper essentially, is the only thing that I need you to submit. I don't really need you to submit the problem set that has the problems because I have those. So that's the problems. I think there's 11 total. You go through those, write your answers here on the answer sheet, and submit your work behind that as your report form for this particular lab. Okay, so this brings us to the end of the video. Let me know if you have any questions. Send an email or post a comment on YouTube, and I'll get back to you as soon as I can.